So last time we were talking about the optical activity, and that is specific rotation and observed rotation. All this stuff we have talked. Now let us see why asymmetric compounds. What is the cause of this optical activity? So we'll see the cause of optical activity. In one word, we can say cause of optical activity is due to the lack of symmetry in the molecule. Compounds which lack symmetry will show optical activity. Compounds which lack symmetry will show optical activity. Now, how do you mean what are the criteria for symmetry? There are three criteria for symmetry, which are known as elements of symmetry. Elements of symmetry. Elements of symmetry, there are three. Number one, plane of symmetry. Plane of symmetry. Number two, an axis of symmetry. Axis of symmetry. And third one, a center of symmetry. A center of symmetry. So plane of symmetry is a plane through which, when an object is divided, will divide them into equal halves. One will be the exact mirror image of the other. For example, if you take a sphere, and if you cut it in any of the plane, say cut in this plane, the upper half will be the mirror image of the lower half. The upper half will be the mirror image of the lower half. So that is what is called a plane of symmetry. The second one is axis of symmetry. Now, there are two types of axis. Axis of symmetry is a line about which rotation of an object by a particular degree will give the original entity. For example, let us take benzene ring. I cut it in a plane perpendicular to you. Benzene ring. Now, imagine a point here. Imagine a point here. You are inserting a rod from bottom, and if you rotate this benzene ring along this axis, every 60-degree rotation, gives you the identical molecule as before. Okay, gives you the identical molecule. So 6 times. So 6 times you can rotate. When you rotate, you will see the original molecule. That 6 is C. Tasni, mute here. Tasni. Fatima, Tasni, mute here. Tasni. Okay. Okay, now. So, if you rotate this by 60 degree, every 60 degree you will get the original molecule. That is, when you rotate this figure by 60 degree, this carbon will reach here. And again you rotate, and that will be original molecule again. Then again you rotate 60 degree, it will reach here. Then it will reach here. So every 60 degree you are getting the original molecule. So how do you get the 60? 360 divided by n. N is a number of sides for this object. There are 6 sides for this. So if you rotate by 360 by 6, that is 360 by 60 degree, you will get the original object. So that axis about which you rotate is known as axis of symmetry. Next, we have center of symmetry. This is now center of symmetry. See here. X. Sorry, I'll put a CL here. A CL here. The point through which, suppose, imagine a point in the center. Draw a line to a group. From this center. Now when you extend it backwards, extend that line backwards. If you extend the same line backwards, you will meet an identical atom. See here, on going to the front, you have met a chlorine. Go exactly backwards if you meet another chlorine, as is the case here. This center is known as a center of symmetry. So these are the 3 criteria for symmetry. If any molecule does not possess this, those compounds are known as asymmetric compounds. So, a symmetric molecule or chiral molecule are molecules with no element of symmetry. Molecules with no element of symmetry. That is what is called asymmetric molecule or chiral molecule. How can you identify them? Okay. What is the criteria and how can you identify them? What is a necessary condition for optical isomerism? Optical isomerism requires optical isomerism is shown by compounds with asymmetric carbon, that is carbon containing 4 different atoms of groups. Is shown by compounds with 4 different atoms or groups four different atoms or groups. So optical isomerism is shown by compounds with 4 different atoms or groups on the same carbon atom. So that is the basic requirement of optical isomerism. Okay. Now we'll take one compound, that is 2-bromobutane. So bromobutane 1, 2, 3. This is butane. This is 2-brom. So these carbon contain 4 different atoms and groups. This is 1, 2, this is 3, and 4. So we have 4 different atoms and groups here. This molecule will show optical activity because its mirror image is not superimposable on the original molecule. Okay. So if a compound contains presence of chirality is a criteria for optical isomerism. Now let us look at, let us draw the structure of this molecule. See here, I have CH3, HBr, and C2H5. And now you can draw the mirror image of this. HBr, CH3, C2H5. So this carbon contains 4 different atoms and groups. So that is what is known as an asymmetric carbon. this way of representation is known as Fisher projection. Fisher projection. Okay, so that is this way of representation. This means that this bond is towards you. It is actually this one. This is darkened. Okay, and so these two are enantiomers. One of them is dextrorotatory, the other is levorotatory, but you cannot say which is which unless and until you have a data in the literature or you know it. It is not possible to predict whether a compound will rotate plane polarized light either towards right or left. It is not possible to say that. So it has to be found by experiments. Okay, the type of rotation. Now let us look at what are enantiomers. These two are enantiomers. This and this are enantiomers. Okay, optically active compounds. In the case of S-butanol, S-butanol, or we have not. S, we can say D-butanol, the dextroliver, the D2-butanol. So the structure is CS3 H C2H5 and OH. And its mirror image is here is the compound. The mirror image, and one is H here. So this is how you represent two enantiomers. Now diastereomers, the definition is very simple. Stereoisomers which are not enantiomers. That is the best definition. Stereoisomers which are not enantiomeric, which are not enantiomers, not enantiomer. Stereoisomers which are not enantiomers, which are not enantiomers. So that is diastereoisomers. A very good way of studying this is to draw the structure of lactic acid. You can see here, tartaric acid. Tartaric acid is CH3 sorry, COOH, H, and COOH. This is tartaric acid. In tartaric acid, we can see we have two carbon atoms. Before we come to tartaric acid, we'll take because there's an internal planar symmetry here. Before that, we'll take a 3-chloro-2-butanol. One second. 3-chloro-2-butanol. Because there is a symmetry in that. Now, 3-chloro-2-butanol, you can draw in different way. 1, 2, CH3, H, OH, Cl, and CH3. 3-chloro-2-butanol. So 1, 2, 3. So this is the chloro, and this is the OH group. Okay. Now, let me draw the mirror image of this. If you draw the mirror image, you get OH, then CLH, CH3, and OH, H here, and CH3 here. Now you can see here, both the hydrogens are on the same side, the substituents are on the opposite side. So hydrogen on the, both the hydrogens on the left, on the first two carbons, you call this as erythroenantiomer. Erythroenantiomer. And these two, where the H is on the opposite side, on the right hand side, it is called trio isomer. Oh, sorry, not this. These two are erythroisomers, where H is on the same side. Both the H are on the same side. Now you take CH3, OH, H, and H and Cl. Okay. Or you can put the other way around. H, OH, H, and Cl, and CS2. So these two are trio enantiomers. Trio enantiomer. So these are, so this is the second designation of optically active compound. Now remember, this should be the least oxidizing group. And then you can number 2 and 3. You can discuss between 2 and 3. but not beyond that. Okay, so for erythro and trio, you have to consider only the group on the second and third carbon from the bottom. Second and third carbon from the bottom has to be considered. So this is to be considered, this is to be considered. So that is erythro and trio. Okay. Now let's see what does the tartaric acid has to say. Okay. Now for tartaric acid, for optical activity of tartaric acid, we have HOH. This is tartaric acid. You can draw 4 forms for this. One is a mirror image of this, which is also erythro. COOH, COOH, H and H. These two forms are mirror images of each other. And you can see here, there is an internal plane of symmetry. There is an internal plane of symmetry for both these molecules. Okay. So this you will classify as meso compounds. As meso compound. Now meso compounds are identical. This does not represent two compounds that are one and the same. Now, the optical isomer of tartaric acid will be like this. H, OH, OH, and H, and COH. So this molecule will show optical activity. Next one, the mirror image of this. OH, H, H, and OH here, and COH. So these are the other two compounds, which are DL mixture, DL mixture. Okay. So that is the optical activity of. So one of these can be separated out. These two are two different compounds. These two are same compound. So diastereomers can be separated into individual components. Diastereomers can be separated into individual D or L isomer. But meso compound being the same cannot be further separated. Okay, right. So meso compounds will show optical activity due to, since they have got a plane of symmetry. They have got a plane of symmetry, and that is why meso compound is optically inactive. Okay, it has got two chiral centers, but still it is optically inactive because of this. right? Now, so I gave you the definition of diastereomers. It is stereoisomers which are not enantiomers are called diastereomers. Stereoisomers which are not enantiomers are called diastereomers. Okay. Now, different methods, different processes involving the optically active compounds. Number one is racemization. Racemization. Okay, I think it is time up. We'll continue tomorrow. ഈ സമയം നിങ്ങൾക്ക് പറ്റുമോ അതോ രാത്രി എടുക്കണോ? ഇപ്പൊ തന്നെ 4 പേരേ ഉള്ളൂ. 4 ഇല്ല, 3 പേര്, എല്ലാരും പോയി. ഇതെനിക്ക് തോന്നുന്നില്ല നടക്കുന്നു അല്ലേ? നിങ്ങളുടെ പരീക്ഷ എന്നാ കഴിയാം? വെള്ളിയാഴ്ച. അതെ, എല്ലാ പേപ്പറും പരീക്ഷ ഉണ്ടാവും.